The evolution of human connectivity has always been defined by a single ambition to transcend the physical limits of how we share information. As we stand on the threshold of the sixth generation, 6G, we aren't just looking at faster downloads, we are looking at a fundamental redesign of reality, a future where the environment itself becomes an intelligent participant in the communication process. Today, we explore the architectures that will make this possible, from antennas that move like liquid to surfaces that compute at the speed of light. To understand where we're going, we must first look at the bottleneck of the present. Massive MIMO brought us 5G, but it has reached a plateau. Scaling up conventional antennas further is no longer sustainable. The cost in power, hardware complexity, and physical footprint is simply too high. We begin with the first pillar of the 6G revolution, metasurfaces. These are not just antennas, they are programmable skins for our world. Metasurfaces are composed of artificial metamaterials. These are macroscopic elements designed to mimic atoms, allowing us to engineer physical properties like permittivity and permeability. These surfaces come in two main types: passive reflective surfaces that shape the environment, and active antenna arrays that can transmit and receive data directly. Dynamic metasurface antennas, or DMAs, represent a breakthrough in antenna design. Instead of individual RF chains for every element, they use wave-fed architectures. Each metamaterial element acts as a resonator. By controlling its oscillator strength and damping, we can tune its response from a narrow filter to a frequency-flat profile. This eliminates the need for power-hungry active phase shifters. Tuning is accomplished with simple components like varactors, requiring minimal additional energy for beam steering. The result is a low-profile, energy-efficient system that can be seamlessly integrated into urban landscapes, indoor walls, and even room ceilings. We are also moving towards cell-free topologies. Instead of relying on a few massive towers, 6G will utilize thousands of small access points working in perfect coordination. Innovative concepts like pinching antenna systems allow us to adjust the number and position of antennas on a waveguide through simple attach and detach operations. If metasurfaces can shape signals, can they also process the information within them? This leads us to stacked intelligent metasurfaces. And SIM is a multi-layer metasurface array. Think of it as a physical realization of a deep neural network, where each meta-atom acts as a reprogrammable artificial neuron. Because processing happens as the electromagnetic wave propagates through the physical layers, computation occurs literally at the speed of light. This allows for MIMO pre-coding and combining to be carried out entirely in the wave domain. We no longer need complex matrix inversions in digital baseband processors. By eliminating interstream interference in the wave domain, we can use low-resolution, power-efficient converters, drastically reducing the complexity of the transceiver hardware. This wave-based approach enables electromagnetic wavefront sensing, which detects signal direction by simply measuring phase shift differences. No intensive digital math required. The applications are profound. SIMs can perform real-time target recognition and velocity measurement by analyzing the backscattered waves as they pass through the layers. In the past, antennas were static. In the 6G era, they will be dynamic, adapting their physical geometry to the environment. Flexible MIMO technology categorizes this shift into three dimensions: where we deploy antennas, how we arrange their geometry, and how they move in real time. Consider movable antennas. By allowing elements to glide along a track, the system can sample the electromagnetic field at its absolute peak, maximizing signal strength. We are even seeing the rise of fluid antennas, where the antenna position isn't just discrete, but can be continuously optimized to overcome fading and interference. Deployment flexibility extends to the sky. UAV-based transceivers and low Earth orbit satellites will use these flexible arrays to provide global, on-demand coverage. Geometric flexibility also means moving away from uniform grids. Pre-optimized irregular arrays can achieve 90% of the performance of movable antennas with far less complexity. To bring all these innovations together, we need a framework that can manage them. This is the tri-hybrid MIMO architecture. It unifies spatial processing across three distinct layers: the digital layer for complex logic, the analog layer for initial shaping, and the electromagnetic layer for final optimization. In this architecture, a single physical antenna port can emulate the behavior of a much larger virtual array, enriching the available spatial modes without increasing hardware cost. While reconfigurable intelligent surfaces act as external mirrors, the tri-hybrid approach integrates the metasurface directly into the transmitter, turning the device into a smart source. Perhaps the most transformative change in 6G is that the network will no longer be blind. It will see the world it serves. ISAC, Integrated Sensing and Communication, merges radar and radio. The same waves we use for data are used to map the environment in real time. Distributed MIMO networks take this further. Multiple access points collaborate to provide diverse sensing observations, overcoming blockages and identifying objects with extreme precision. By operating in the millimeter wave and terahertz bands, 6G systems can achieve sub-millimeter radial resolution, turning the network into a planetary-scale microscope. This enables the creation of wireless digital twins, highly accurate representations of the environment that allow the network to proactively optimize itself. For autonomous systems, this means near-perfect spatial awareness. Robots and vehicles can navigate complex environments with zero onboard sensors, relying entirely on the 6G web. To make all this possible, we need three vital enablers: efficient channel acquisition, low-complexity design, and explainable AI. Channel prediction uses machine learning to forecast future signal behavior based on historical data, allowing the network to proactively adjust before a problem occurs. Channel mapping creates a site-specific dataset, allowing 6G systems to understand the unique propagation features of a building or a street corner before a signal is even sent. And with explainable AI, or white box AI, the optimization process becomes transparent. We can see exactly how the network makes decisions, ensuring reliability and safety. We are moving toward an era of infinite connectivity, a world where the digital and physical domains are no longer separate, but are woven together into a single intelligent fabric. From metasurfaces that compute to antennas that move, the architecture of 6G is a testament to human ingenuity. It is a fundamental redesign of how we interact with our world. Welcome to the 6th generation. The future isn't just coming, it's being built, one wave at a time. Let's take a closer look at the physics that makes this possible. At the core of every metasurface is the unit cell, a structure smaller than a wavelength. By adjusting the bias voltage to these cells, we can independently control the phase and amplitude of every reflected wave. This is the ultimate level of signal control. This enables holographic beamforming. By creating a precise interference pattern across the surface, we can form pencil beams with near-zero leakage into other directions. In the stacked intelligent metasurface, these layers work like a physical computer. Each layer performs a linear transformation on the incoming wave. As the wave diffracts through multiple layers, it effectively executes deep learning algorithms. It is a computer made of light and metal with no moving parts. The energy efficiency is staggering. While digital processors consume gigawatts to handle massive MIMO math, wave-based computing does it using only the energy of the signal itself. Real-time geometric flexibility is critical for high-speed scenarios. In a world of bullet trains and drones, antennas must shift their focus in milliseconds to maintain a link. We achieve both macro and micro diversity. Macro diversity from distributed networks and micro diversity from the ability to move individual antennas to the perfect spatial point. Operating in the terahertz range brings challenges. Molecular absorption by the atmosphere means we must carefully select transparency windows for long-range communication. But the payoff is resolution. THz waves are so short they can map surfaces with sub-millimeter precision, allowing 6G to feel the texture of the environment. Graphene will be the heart of these sensors. Its high electron mobility and tunable conductivity allow for extremely efficient reconfiguration at terahertz speeds. We are also exploring MXene materials. These offer unique electronic properties and exceptional flexibility, potentially replacing gold in the next generation of metasurfaces. This is the backbone of immersive AR and VR. The network provides the spatial data and the massive bandwidth needed to render photorealistic worlds in real time. Security moves to the physical layer. By measuring the environment, the network can identify eavesdroppers and actively hop the wavefront around them, making data interception impossible. And for the billions of IoT devices, 6G offers the dream of zero-power sensors. Metasurfaces can collect and focus ambient waves to power the sensors of the future. Technical enablers like channel extrapolation allow us to activate only a few antennas to understand the whole array, saving massive amounts of power and training time. Distributed processing delegates the math to the edge. Access points handle local beamforming, while the central cloud unit manages the global network strategy. By leveraging the signal superposition property of wireless channels, we can perform over-the-air computation, aggregating data from thousands of sensors instantly. Standardization efforts are already underway. 3GPP Release 19 marks the start of the official 6G journey, ensuring these technologies are globally aligned and interoperable. The roadmap is clear. We are moving from theory to testbeds, and from testbeds to the global standard. The transition to 6G will redefine the next decade of human progress. This is not just a technological upgrade, it is a masterpiece of interdisciplinary engineering, combining physics, mathematics, and computer science. A unified world where information flows as naturally as light. A world where every object is an intelligent node in a global web of connectivity. The impact will be global, democratizing access to high-speed intelligence and enabling sustainable growth in every corner of the planet. From the speed of light computing to the geometry of movement, 6G is the architecture of our future. The future is no longer a destination. It's the wave we are building together. Stay connected. Managing thousands of meta-atoms requires a sophisticated control loop. The base station and the meta-surface communicate in real time, adjusting weights to maintain a perfect link. Beyond speed, 6G enables precision. Remote surgeries will become a reality, where surgeons can operate from across the globe with tactile feedback and sub-millisecond lag. Education will be transformed. Holographic classrooms will bring students from every continent into a single shared space, breaking down the barriers of distance and cost. Finally, 6G is a commitment to our planet. By using passive metasurfaces and wave-based computing, we can reduce the global energy footprint of our networks by orders of magnitude.